So hi, I'm Miles Berry. I work at the University of Roehampton training the next generation of outstanding teachers. We do a lot of scratch programming with our trainees. We get them to do a lot of scratch programming when they're out in school working with typically primary age pupils. But a lot of the work I've been doing this last year has been this Project Quantum thing, which is a funded project to develop a national item bank of multiple choice questions about addressing to assess students' learning, pupils' progress in computing, the whole host of that, some of which relates directly to Scratch. But what I want to do for the session this afternoon is give a much broader survey of approaches we can take to assessing learning, assessing progress when it comes to Scratch. Essentially, the challenge for assessment is we want to see what learning has happened within the young person's brain. What have the changes been to the neurons and the connections between the neurons in there? But you can't do that directly. It requires special equipment and special training, and the risk assessment takes forever to complete. So we have to go through one or other, or possibly both, proxy measures. You can set projects or look at projects and see evidence from the projects of what it is that the student has learned. And if you look at a project at the beginning of September and a project at the end of July and see, oh my gosh, look at how much more complicated the ideas are or how much more efficient the code is, then there perhaps is evidence of progress of learning having taken place. The other approach, of course, is to ask young people, the learners, some questions. I think I've come to the position that that's actually a really very useful way of getting at their knowledge, their understanding of some of these deep ideas in computer science. I think, though, we're talking here about two alternative paradigms to assessment or to education. If you take the project-based approach, that fits so nicely with our constructivist, Papert-inspired mindset of we learn best through making things to show to others. We nod in the direction of Piaget, we nod, of course, in the direction of Papert there. We might use criteria to assess in some sort of reasonably systematic, objective way what there is evidence of in the project. It's a very sort of practically focused approach to computing education or to education in general. We're perhaps looking at the skills of using one particular set of tools here to do something interesting, and our judgments might be on the qualitative side of things. Oh, that's really interesting. I love the way they've done that. I like the way they've talked about that. The alternative approach, the question-based approach, places it perhaps much more in a positivist mindset of the truth is out there, and we have a body of knowledge to pass on to our learners. We might take a behaviorist approach of stimulus, response, reward. I'm going to ask you a question. If you get it right, you will get a biscuit. Biscuits are not actually provided here. We look at Skinner as our sort of theorist here of how to teach by asking questions and rewarding the right answers. We might be less interested in criteria than some sort of score, or possibly perhaps some scaled score, making it possible to make a comparison between two learners or between one learner at 2 points in time. We might see this as having a more academic focus, again, the body of knowledge being passed on. We might try and take a more quantitative approach. Now, you can't really hold both of those mindsets in your own mind at the same time. You can't say the truth is something we construct and the truth is out there. But if you're willing to make that sort of philosophical, put that to one side, I think both of these approaches have a huge amount to offer pragmatically when it comes to what we actually do in the classroom. Okay. So my justification for that is to say capability when it comes to computer programming, when it comes to coding, is a combination of the knowledge of the ideas of computer science as well as their application to the practical task. This isn't just computer science, it is also software engineering. It is not merely theory that we're teaching, it is also practical skills of building something for other people to use. So let's start then in that sort of project-based approach, the project-based paradigm. The key work here has been done by Karen Brennan and Mitch Resnick back in 2012, this new frameworks for studying and assessing the development of computational thinking, and they see computational thinking as having these three components: the concepts, the practices, and then the perspectives that gives you on the world. They talk about this in terms of computational thinking, but if you look at their concepts, things like sequences, loops, events, parallelism, conditionals, operators, and data, they're actually very, very close to the metal. This is stuff which is actually much more closely associated with the specific domain of computer programming than this more sort of amorphous Computational thinking, it's a way of solving problems. These are concepts of programming rather than concepts of problem solving, I would suggest. Their practices do, again, relate specifically to computer programming as an outworking of this computational thinking, although I would say they're not confined merely to that domain. Back in England, for barefoot computing, we've taken that idea of the concepts and the practices, we call them approaches, but actually taken this step away a little from the practical experience of programming and thinking about computational thinking. We talk about the concepts of logic, of algorithms, of decomposing problems into smaller parts, of looking for patterns and using similarities, of, yes, putting to one side the unnecessary detail and, of course, making judgments about whether something works or not, as well as, and I think really importantly, the approaches which a programmer engages in, making, tinkering, playing, experimenting, making something, fixing things when they go wrong. They go wrong a lot with my programming, keeping going when it goes hard, and yes, working collaboratively in teams, although not, of course, for the controlled assessments for exams. I think we have there this idea of programming itself is the two-step process of how are you going to solve the problem, the algorithm, the computational thinking, and then the practical outworking of that as writing that idea, that algorithm, in some particular language which the machine will understand. Scratch, snap. I think other languages are also available. Okay? How do you go about assessing computational thinking? Brennan and Resnick say 3 ways of doing this. Look at the portfolio. Have a look at not just one project, but the portfolio of projects that the student has produced. And back in the time when they were writing the paper, there were automated tools which would show you this learner has used this block in their portfolio. If there's no repeat block, then can you really say that that learner has any understanding of the concept of repetition? They also talk about artifact-based interviews of meeting with the student, the learner who's produced the code, and asking them to explain it, asking them to talk you through what they've done, as well as setting the challenge. And we move into, I think, something closer to that question territory of setting a particular design challenge and seeing how the learner responds to that. They analyze those and they conclude with progression from the first approach, that project analysis, to the design scenario appears to be predictive, mainly by leading to a more nuanced understanding of a Scratch's fluency, with computational concepts having access to richer data about a Scratch's computational practice, setting the challenging task rather than just looking at what the learner produces. Jan Harrison, when we were talking about how to go about assessing our new English computing curriculum, talks about this idea of the design interview at the end of the project. Set time aside with each learner to ask them questions. Compare and contrast what you've done with another approach to this. Why have you done this? What have you just done? Why have you chosen to do this way? And so the rich data you get from those interviews, I think, inform assessment very effectively. In terms of criteria to assess learning, we have a number to choose from. The lovely thing about standards is how many there are. For the English national curriculum, we have at the end of each key stage, so that's age 7, 11, 14, and 16, the expectation that pupils should know, apply, and understand the matter, skills, processes specified in the relevant program study. Very vague, you may say, but believe me, tremendous improvement on what went before that. Okay, so here's a body of knowledge that we as teachers should have taught. The end of the key stage, those key points in the child's school career, have they learnt the things that they should have been taught? What sort of things should they have been taught? Well, just looking at programming concepts by the age of 11, they should have been taught how to design, write, debug programs that accomplish specific goals, controlling or simulating physical systems, solving problems by breaking them into smaller parts, a little bit of computational thinking going on there, use sequence selection, repetition in programs, work with variables, various forms of input and output. You could look at a Scratch project and tell me, with probably just running the thing, maybe not even having to look at the code, whether there is evidence of sequence selection, repetition, input, output, and working with variables. Yeah? If you find evidence of all of that in a Scratch project, then surely you can just tick the box to say the learner has learnt that requirement, those criteria are satisfied. That doesn't mean to say everything that satisfies those criteria is equally good. But there's evidence that they've learnt the things that they should have been taught. Just published, I think 2 weeks ago, CSTA, Computer Science Teachers Association, the US equivalent of Computing at Schools, have produced their definitive 2017 standards. And this is the grades 3 to 5 criteria for programming, which covers similar territory to what we have on the English national curriculum, but goes a lot further in terms of the human processes that are involved in computer programming and software engineering. Observe intellectual property rights. Give appropriate attribution when creating or remixing programs. Don't you think that's lovely that that's one of the criteria? And again, you could look at a Scratch project and start ticking off. There is evidence that it meets each of these criteria. I've done a similar thing for a scheme of work that I wrote for a UK publisher, Rising Stars. This is switched on computing. We've said, for each of those criteria on the English National Curriculum, let's award the badge. Like they do assessment in Scouts, Cubs, Brownies, Guides, here's a list of what you have to do when you can put together a portfolio that demonstrates those things, show it to the person leading your pack, platoon, whatever they're called, and get the badge. For each of the units in Switched On Computing, we have the criteria there, so can you correct mistakes in your animation program? Yes, that's evidence of the problem solver badge. Can you create your own sound and graphics for the sprites and the backdrop? Yes, that's evidence of the creative producer badge. And then you have the complete set of criteria. Here's Programmer 2 at the age of 11. Very similar language to what I just talked about. To earn this badge, you will need to show that you can use sequence, use selection, use repetition, work with variables, work with various forms of input and output, and put the onus onto the learner to put together a portfolio to document how they have demonstrated those things which are on the published list of criteria. And if we had more time, we could have a look at this Scratch project and see how it does. That is a drill and practice maths game. And of course, we've got a sequence of instructions there. We've got repetition, it's going to ask a number of questions. We have selection. If you get the answer right, you get well done. If you get the answer wrong, not so much. Input is text. Output, well, we've got graphics. I think we have sound in this one. Variables, we're keeping track of the score. We're keeping track of the position and so on. So you've got all of that going on in one simple Scratch project. More general criteria for assessing progress in programming. John Woolard for Computing at Schools put together this generic list of how to look at a program, what to say about a program that a learner has written, such as on the screen there. We might go a stage further and say there's some sort of progression there. At a very basic level, particularly if you're working in a text-based language, is it syntactically correct? Will it compile? Will it run? We generally don't have to worry about that so much in Scratch or Snap. Is it functionally correct? Will it do what it's supposed to do? Will it pass the unit tests if you've written unit tests? Is it well formatted? Again, Scratch, Snap almost deal with that, but there are ways of presenting a program. Is it the most efficient way to solve the problem is a big question. And then we move into territory like literate programming. Is it an elegant solution to the problem? And maybe even, is it an innovative solution? I've spoken with folks who are lecturing computer science at university, and they say, we don't really want innovative solutions. Innovative solutions, we're never sure whether they're going to be right or not. You know, it's learning the craft rather than being creative, which counts. I don't know. For CS50, which is Harvard's introductory course on computer science, they have this lovely thing in the rubric for assessing students' programs about the design of the program. Yes, it has to do what it's supposed to do. It has to pass the unit tests. It has to also be well-formatted code. But it also has to, for full credit, be well-designed. To what extent is your code written well, clearly, efficiently, elegantly, logically? And questions such as this for those who are marking the assessment. Is there repetition that could be eliminated? Are there loops here that could be eliminated? Are there magic numbers, hard-coded constant values? So there's an extra bullet point crept in there. We have examples of this. So here you go. Write a program which asks for an amount of money and returns the smallest number of coins to make it. So if I said 8 pence, or 8 cents, I suppose, that would be 5 pence cent piece, a 2 cent coin, and a 1 cent coin. 3 coins is the smallest number of coins to make 8 pence in English coinage. You know, how would you tackle that? You got time? Let's move on. Okay, so here are 3 solutions. So this, it works. It gets you the right answer, yeah? It's a whole load of if statements, okay? And it's a greedy algorithm. You know, we take off the £2 coins, and then we take off the £1 coins, we take off the 50p pieces. Obviously, you've got exactly the same, almost exactly the same, code happening inside each block, so abstracting that out as a procedure produces a much more elegant. But if you sort of step back from the greedy algorithm and think, actually, this is just sort of integer division that's going on here, we get a very different solution. There is no ifs and thens here. If we're using those criteria for checking whether you've learned something, this program, the third one here, has no selection statements. So this would not satisfy the requirements of Key Stage 2 in the English National Curriculum. But I would argue that's a much better solution to the problem than this. You may feel differently. You may feel it's not a better solution because it's using, I don't know, funky coding magic or something there. Who's using Dr. Scratch already? Splendid, 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 splendid. Dr. Scratch is really very, very nice. Okay, so you give it a project, the URL of a project, and it goes off and sees, okay, there's evidence of this particular computational thinking concept there. So, whereas we say, okay, in that Scratch game, we can see that they're using repetition, we can see that they're using parallel, Scratch's parallel features, Dr. Scratch will do that sort of static analysis of the code for you automatically and give you a report and give the learner advice on how they could move their coding forward. If you look under the hood, you see the rules that Dr. Scratch is following. So to get the basic level for synchronization, there should be a wait block. To get the proficient level for synchronization, there's a wait until, there's a when the backdrop changes, there's the broadcast and wait functions there. So as a learner masters more and more of Scratch's tools, they make their way forward through that sort of ability to provide a portfolio of evidence that Dr. Scratch will see when it comes to analyzing their code. We're doing a similar sort of thing with our trainees at Roehampton. As part of their process of training them to become primary school teachers, they have to do a little bit of programming themselves. So they take a children's book, for instance, the Gruffalo, for instance, one of the Harry Potter texts, the Hungry Caterpillar is great, although Eric Carle is apparently quite litigious about his images, and write an educational game using that text as a starting point. And we have criteria for what they should be able to do in their programming. So a user interface that's appropriate, range of interactive problem-solving activities, original sound and graphics. So we're taking a criteria-based approach. And they produce some gorgeous pieces of work in response to that. I'm not going to play the code here because of time pressure, but you've got an illustration of the sort of thing that they'll make in response to one of these challenges. So very much a criteria-based approach to assessing projects. So, all well and good. It's very much in our sort of comfortable, we think Scratch is about creativity. We think learners learn through making things to show to others. What then is the alternative? Well, perhaps asking questions. So there's been a big change in English primary schools' approach, or English schools' approach to assessment. We had that sort of criteria-driven approach. The new wisdom from on high, this Macintosh report on assessment without levels, recommends that rather than trying to recreate levels by the back door, we establish this national item bank of assessment questions, used for formative assessment in the classroom and to help teachers evaluate understanding of a topic or concept. And indeed, for summative assessment at the end of the key stage, can you answer these questions correctly, is a very different approach to assessment to show us the best thing that you can make in Scratch. And let's be impressed by that, okay? Different philosophies driving these two approaches to assessment. Be aware of that. But asking questions is really efficient. Marking a whole stack of Scratch projects will take forever. Well, not forever, but a long time, okay? Giving children some automated questions to answer and seeing whether they get them right, really efficient. I'd say both and rather than either or. Daisy Christodoulou was part of that panel. She says, don't let the criteria drive what you're doing. Let the questions drive what you're doing. By the end of the year, your learners should be able to answer these questions, respond to these challenges correctly. Very different approach to going about this. But isn't this a little bit similar to what we do in software engineering, in test-driven development? Who's familiar with test-driven development? Okay, that's not enough of you for me to be able to skip the explanation. So in software engineering, test-driven development, you've got software that does a thing, okay? The client comes along and says, oh, that's great, thank you very much. Wouldn't it be nice if it also did this thing, okay? You're tempted at that point to go and write the code for the new thing. Don't in test-driven development. Talk to the client, get them to say exactly what they mean by this thing to a level of detail that you could write a program to test whether your code does the thing or not, okay? Throw your code into that test program, and it should fail at that point, okay? If it passes at that point, then your code already does the thing you've been asked to do, and you can just go straight to sending the invoice out, job done, okay? But if it doesn't pass at that point, you've got to go off and write the code to do the new thing, the new feature. then test again, and because you're a brilliant coder, it will pass immediately at that second time you apply the test, okay? So at that point, look, here's evidence that my program does the thing you asked me to make it do. Then you can send the invoice, okay? If it doesn't pass at that point, go and write your code better, okay? Or fix your code, debug your code. Okay, you may not be quite ready for sending the invoice out straight away. You might want to do this sort of refactoring, making it better integrated, making it fit better with the rest of the software that you've written. That's all very interesting, Miles, but what's that got to do with teaching? Well, can we not do the same thing over in our line of work? If we're asked to teach a group of learners a new thing, then the first thing we should do is not teach them the new thing, but test whether they know the thing already. If they do, you don't need to teach it, okay? You can go and have fun, make something, do something interesting, okay? If they don't know it, then go off and teach the thing, test again, and they should know the thing at that point, okay? And there's evidence, if you're asked to provide it to, I don't know, school administrators or school inspectors, of progression. They couldn't do it, I taught it, they could do it. I've done my job well. Don't just rest on your laurels at that point, but better integrate it into their existing mental schema. Teaching to the test, well, perhaps, but if they're good tests, may not necessarily be a bad thing. And we have some lovely questions. Who's seen Project Euler? Okay, a huge bank of programming challenges, okay? Not the sort of thing you would immediately think, oh, Scratch is going to be great for that, because in Scratch we tinker, we make, we create. But we have, things which may be seen by many as relatively dull compared to these lovely Scratch projects. If we list all the natural numbers below 10 that are multiples of 3 and 5, we get these. Sum of those is 23. What's the sum of all the multiples of 3 and 5 below 1,000? Think in your head now, how would you write a Scratch program to do it? It's easier in Snap because you've got all of the lovely functional programming tools, so just add together anything which can be divided by 3 or divided by 5 in the range 1 up to 999 inclusive, okay? And we get an answer out from it using that code. Similar things, this is a Haskell challenge, find out whether a number list is a palindrome, read the same forward as backwards, and that's one version of code that would do that in Snap. Okay, so responding to a question like this, yeah, we're really quite laser-like focus on can you think through how to solve these problems and can you write good code to solve those. Then we can do the code tracing thing. So here are a couple of programs. Pick one of those and figure out for yourself what it would do. Step away from the computer, okay? You could just copy that in and click the green flag and see what happens. But it's much more interesting as a test, I would say, of computational thinking, possibly of coding, to be able to predict from this what's going to happen. Anybody figured out this one? Okay. Fingers moving in the hat. That's great, okay? Anybody figured out this one? Okay, the reveal. Let's have a look at these. Okay, so we get square around 10 squares. Yeah, did you get it right? Okay. And this one, of course, is one of these lovely fractal trees, but I think it's gorgeous when you set the 90 and the 180 in there. You get this sort of wonderful sort of geometric pattern out of this. So we have these Parsons problems. Before I discovered Parsons problems was the proper name for this sort of thing, I called these Scratch Jigsaws. So here are all of the bits of code you need in order to make a program that does something. In this case, it's an implementation of binary search. It's the guess my number game played by the computer rather than by the player. So Scratch will guess your number. And then we have the challenge of how do you fit those together in order to make the thing. This Parsons problem idea goes back at least as far as 2006, and there's strong evidence that this is a motivating challenge for those who are learning computer science, at least at undergraduate level, as well as very, very effective at helping them to understand some of the ideas here. And then, of course, the debugging challenges. This one, we have the car trundling around the track there. It's great, it's fine, it does what it's supposed to do. You increase speed from 3 to 10 and it will veer off the track. Is that a bug? Is that a feature? I don't know. It could be teaching something really important in driver ed. If you drive too fast, you will lose control of your car. How do you fix that? Well, you could just keep the speed low, or you could increase the angle of turn. Or you could do something really very, very subtle about writing a block which tests not just at the end of moving forward speed steps, but at each point of that journey, whether it's gone off the track, and use that, okay? And then the code analysis thing. Here are 3 algorithms for finding the highest common factor, the greatest common divisor of a pair of numbers. Which of these is going to be the most efficient way to do it? The test every number one at a time. Sorry, that's the test every number one at a time, or the ladder method or Euclid's algorithm for finding highest common factors. And of course, it's Euclid's algorithm for finding highest common factors. If you've not seen, it's Michael Ball's Lambda, which is written for Snap, written for Beauty and Joy of Computing. I think he's talking about it tomorrow, and there's a poster presentation tomorrow. This is unit testing for Snap. Write Snap code which meets the particular criteria, and it tests whether the criteria are met. I want to finish by talking a little about multiple choice questions, which have had a bad press. There are lots of ways of using these, so you can use them at the hinge point of your lesson. I've introduced an idea, and I need now to figure out whether the students I'm working with have understood the idea. I need to do that rather than just picking on one or two people and saying, what do you think is the answer? To the whole room. A multiple choice question is a really very efficient way of doing that. Hold up the answer card A, B, C, or D, depending on what you think is correct. If everybody's got the right answer, then move on. If loads of them have not got the right answer, if there's a particular misconception, then move back. They use this in the States in undergraduate computer science education as part of this peer instruction approach. So put the question on the board, get everybody to think about it. Then, before you show the answers or the graph of results, get them to talk to their friend and agree as a team on an answer which they all wish to vote for. Then vote again, show the graph, and have the discussion in plenary. And there's evidence when they've done this with undergraduate computer scientists, this really does work, including preparing for traditional pencil and paper tests. So we've taken these ideas to heart for this Project Quantum stuff. We've got the great and the good working on it. Tim Oates, great guru for English curriculum, he was the guy who chaired the panel on the revision of the whole of the English curriculum. Simon Peyton-Jones, who's chair of computing at school and the man behind Haskell, and Prof. Rob Coe up at Durham's Centre for Evaluation and Measurement, one of our gurus on assessment theory, and they're part of the team on this. What we're trying to do is put together this free bank of questions. It's free in the three senses. It's free beer. You do not have to pay to use any of this, okay? It's free speech. We're setting the bar very, very low. If you want to write a question on that, you can put it on the platform, okay? As long as there are no rude pictures, no rude words, and the correct answer is indeed the correct answer, okay? The criteria are very straightforward to meet. It's also free for you to use it how you want. If you don't want to use it on our platform, have the question, put it onto your own platform, that's fine. It's also kind of free in the sense of free kittens, in that we're not doing all of this for you. There's work involved in making this something which you can use with the learners in your class. So it's formative assessment only. The students can see the questions in advance, okay? They can't see the quizzes you're going to use, but they can look at all 4,000 questions if they want. We think that's fine because doing lots of questions really helps you master the material. It's an online thing, it's automatically marked, so the time you spend selecting the questions you save on marking their work. We're aiming for high quality, more of that later, and it's about supporting teaching, not assessment as a goal in and of itself. Here are some questions. This is a scratch question, all right? I'm going to make you choose one of the answers here, okay? So here's the question. You put a little scratch block here, say 0 divided by 0. What will Scratch say is the answer to 0 divided by 0? 4 possible answers on the card there. Infinity, 0, 1, or nan, okay? And I'm going to count down from 3. When I get to 0, could you all just call out A, B, C, or D? Got it? Here we go. Yeah? Oh, just wait. Okay, 3, 2, 1. B. I'm getting B's. Okay, I'm getting 0 because it's 0 divided by anything is 0. I've got a D. Why is it D? You know this? Okay, it is D. You're absolutely right. Oh, Scratch knows about infinity. If you ask 9 divided by 0, it will say infinity, which I think is slightly misleading, because it could be positive infinity or negative infinity, and they're whole way apart on the number line in my experience. But not a number is the correct answer to this question. It's mathematically an undefined question. So Scratch implements, tell me the correct number, IEEE 7834 or whatever it is, transfinite arithmetic, which I think is pretty cool, okay? More Scratch questions. This is a famous question in the history of computer science education. You write this in C, I think it was, A equals 10, B equals 20, A equals B, and students get it wrong a huge amount. undergraduate introductory computer science courses. You put it in Scratch, and our evidence on the quantum platform is everybody is getting it right. It's a pointless question to ask, because Scratch's syntax is so much more expressive than C was. Which of these these Scratch programs would draw an equilateral triangle? What are the misconceptions? And of course, it's the 60 versus 120 thing, yeah? Is it the interior angle or the exterior angle that the turtle turns through? And then you can go a long way with the simple multiple choice question. So here's an attempt to implement selection sort in Scratch. It doesn't quite work. Where's the bug in the code? Okay? And to solve that, you've really got to know what you've got to think through selection sort, okay? Put yourself in the place of the cat interpreting the code. What do we think makes a good question? One that you can answer quickly. It shouldn't be one that you have to spend the whole lesson working out the answer to, so that last one might not be brilliant. Multi-step is really bad because you can't tell where it was that the learner went wrong, and so you don't learn anything from the wrong answer. You should be able to learn something from the incorrect answer, and it shouldn't be possible to get the correct answer while still having key misconceptions. This, of course, is a nonsense, because we know that monkeys will get multiple choice questions right 25% of the time. Okay, so we're hoping for more than 25. We're interested in higher order thinking skills. A lot of the early questions on quantum were of the form, which of these is the correct definition of algorithm? We think that's not a particularly helpful question, yeah? Some of the ones I've just shown, hopefully, are more helpful. Next September, this September, in fact, we're going to provide much more detailed feedback to question authors and to teachers about how students are getting on. In this sort of assessment theory thing, there's this rash analysis which says, once you have enough learners doing enough questions, you can start looking at how the two are interrelated and saying, okay, for the more able students, this is a question which they get right lots of the time. For the less able students, they're not getting it right. So it's a good discriminator between those who've got the construct and those who are still working towards it. There is no time for discussion, but I've got an email address on there, and I'm going to be around for the next 2.5 days. Thank you so much. And Paul, I'm sorry I've eaten into so much of the time. Thank you.